This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Hello, this is Stefan Tilkov for Software Engineering Radio. My guest today is Adrian Cockcroft. Adrian is probably best known for leading Netflix's efforts to move to a fully cloud-based, highly dynamic architecture. He also worked as a distinguished engineer at Sun Microsystems and co-founded eBay's research labs. Today, Adrian works as a technology advisor for Battery Ventures. Adrian, welcome to the show. As usual, I would like to ask you to start us off by introducing yourself. Who are you and what do you do?
Hi there, thanks for having me on this show. So I'm a technologist and software developer, been around for a long time. Let's sort of just start from the beginning. I started off with a physics degree based out of the UK and worked for about 5 years as a software engineer. That's my job title, so that seems to line up with the podcast. Building embedded real-time systems and kind of all kinds of different kinds of software, but for a company called Cambridge Consultants in the UK. We were one of the first users of Sun Workstations as our development platform back in the mid-80s, and eventually Sun opened an office nearby and I joined them. So then spent about 5 years as a systems engineer at Sun in the UK, and then moved to the US about 20 years ago and worked through different parts of engineering at Sun, basically concentrating on performance and capacity planning. Towards the end at Sun, I was a distinguished engineer basically around that performance capacity planning topic. I wrote a book called Sun Performance and Tuning that a lot of people have, which has a nice picture of a red Porsche on the front, which most people remember it by the cover rather than the title. And the last job I had at Sun was the chief architect for high-performance computing. And in 2004, Sun did one of its shrinking laying people off phases, and that whole group got laid off. So then I joined eBay. I'd worked with eBay a bit on and off over the years, helping them scale. So I worked there as basically a sort of distinguished availability architect or something, I think was the title, working on scaling and availability. I learned a lot about large-scale systems and customer-facing systems rather than enterprise, selling to enterprises. I helped form the eBay Research Labs, did some interesting work there. Then in 2007, I joined Netflix. And I think Netflix is on the verge of launching in Germany and France in the next sometime in the next month. So that'd be interesting to see how that rolls out. But I joined Netflix and managed a team of software developers for about 3 or 4 years. Towards the end of that period, we decided to move to the cloud, and I led the team, or one of the teams that moved the part of the platform to the cloud. We then formed a platform team within the company, and I became the architect for that team and started going out and doing talks outside Netflix, explaining to people, this is how we did cloud, this is what we're doing, and the reaction to that started off as incomprehension, worked its way through denial to, okay, this looks useful. And finally, at the end of last year, there was getting quite a lot of interest outside Netflix, and I moved to work for a venture capital company called Battery Ventures. And that's been the last 7 months or so, where I'm doing a similar kind of thing. I'm spending a lot of time at conferences explaining, talking about new technology. And I'm spending a lot of time with the portfolio companies that Battery's invested in, helping them scale, become more available, move to cloud, and just generally, see if I can get them to be more valuable more quickly. So that's what the VCs care about.
Okay, so it's really hard to it's hard to read an article or to read any sort of article these days that doesn't somehow mention the cloud or cloud computing. Despite that, how would you define those things? What is the cloud, and what does cloud computing actually mean to you?
I think the biggest change, if you're working in a company and you think, I need some machines to do something, and you have to file a ticket and wait until somebody else to get around to sorting out that ticket. At some big companies, that takes a month, 2 months to get just a single machine. The real thing about cloud computing is it's self-service. You make an API call and a bunch of machines turn up a few minutes later. That's the most fundamental difference. It speeds up the whole procurement cycle, and it means that you can give machines back because you can get them back again in a few minutes. So it makes everything much more dynamic. You can use the cloud as just a faster way to do the things you used to do in data centers. But the really interesting things come when you start realizing what happens when you use it in a much more dynamic way and machines become ephemeral. You can turn them on, turn them off, and use a machine for a couple of hours, give it back. That's really the essence of cloud. I think it really comes down to putting self-service tools in the hands of the developers to go do things themselves and making what operations used to do into an API. I don't really care whether it's public cloud like AWS or a private cloud inside the company, as long as it sort of should be on demand and there should be enough capacity there that whatever you need to do, it's just there.
Mm-hmm. So that would limit the private applicability to companies that can afford to offer so many machines physically that it makes this possible for almost any kind of thing that developers could think of?
I don't think it limits it. I mean, if you ask for 1,000 machines and you don't have 1,000 machines, you're still going to have a problem. And it's possible to run out on AWS. One of the advantages of public cloud is that you're pooling a much larger piece of capacity. So think of it as being a small fish in a big pond, and it really works well when you are a small fish in a big pond. The alternative, I have a little diagram somewhere, is a shark in a paddling pool. Sharks don't fit in paddling pools. If you end up being a really big user in a really small cloud, it doesn't matter whether it's public or private, it's just not going to work so well. So just think of it as the statistical averaging of lots of different use cases into a big pool of resources makes it look as if it's sort of effectively limitless, but that only applies up to some kind of scale.
Mm-hmm. So how did Netflix end up moving to the cloud? What's the history behind that?
The history is that Netflix started off as a DVD shipping company. It wasn't even seen as a very big technology company at the time. When I joined, they were well known for personalization algorithms as their main sort of interesting technology, rather than scale or anything like that. And they had around 6 million customers when I joined in 2007. And those customers, typically every weekend, they would pull up the website, decide what DVDs they wanted to have shipped in the next and what order by shuffling their queue. And then every time they sent a disc back, we'd send them another one. So the interaction with Netflix was sending a disc in through the postal service. That required a few tens of web servers and a few back-end machines and a big database. It was a very monolithic, centralized app. So that was 2007, and in 2007 we launched streaming with a very small catalog, but it started to take off quite quickly. Now, when you interact with the streaming service, every click has to go to the website. Every time you decide you want to watch something, you browse around the website, you click play, then there's a lot of traffic that goes back and forth, figuring out what to do, finding the machine, finding the movie, giving you a security key to decode that movie, and then logging the activity so that we can make sure that there's good quality of service. Are there any rebuffers? What speed are you running at? Which CDN are you talking to? So there's the number of transactions to the back end is maybe 1,000 times higher than a DVD service. It's some large number of orders of magnitude more traffic, which was fine when we were just starting out with just a small number of machines, a small number of movies and not many customers using it. But the usage rate started to increase very rapidly because there was nothing stopping you from watching lots of movies. You didn't have to send the DVD back and wait for another one. So we started getting a lot of people doing sort of binge watching of content. So So the number of interactions people had with Netflix, the number of things they watched went up, and the number of interactions with the website per view went up by a huge amount. So that basically meant that we looked at our data center, and this small couple of machines in the corner that were put in to initially launch streaming were just running out of capacity incredibly quickly. And in 2008, there was a big outage that Netflix had where the central monolithic app broke, and it was actually the storage problem, the corruption in the SAN, corrupted Oracle, and it was a big mess. And as a result of that, we basically decided we weren't very good at running stuff in the data center, and they started looking out for how are we going to scale this incredible future workload where we didn't know how fast it was going to grow. And that really comes down to the core of why this was interesting, was we couldn't predict how much capacity we're going to need. And in 2009, we moved some of the back-end batch workloads, like encoding movies, to the cloud. And in 2010, moved the front-end website to the cloud. In 2011, moved the database backend so that the master copies of all the data are in the cloud. And in 2012, started open sourcing the tooling we'd built to do that. I guess that's probably the main history points.
So I'm just assuming that you would probably agree that it was the right decision for Netflix to do this in hindsight. Yeah. Would you recommend it to others as well? How dependent is it on being in that kind of business that can essentially grow in a totally unforeseeable way? How dynamic do you have to be able to make sense of that move?
Well, it's certainly more fun to be working at companies that are growing fast, right? If you want your shares value to go up. So if you've got a very static workload or slowly shrinking workload, it's and your app isn't changing very fast, it's probably best to just leave it alone. Then, and the DVD business is still running on the monolithic platform on the big old IBM P-Series machine on Oracle, and I don't think they've changed the code in that for the last few years. But it still has. In fact, it still now has 6 million users. The DVD business, I think, peaked at about 12 million and then went back down to 6. Netflix now has 50 million users on streaming. So, that's what drove it, was this growth. So you can optimize if you have very predictable workloads, but predictable workloads are somewhat boring places to work at. So, yeah. So there's two kinds of ways you can think about a business. If you become a commodity and a utility, really, then you want to optimize for cost, and you're just looking for efficiency and cost and predictability. And there's a lot of technologies you can apply to that. But in a lot of businesses now, the world is moving so fast that what really matters is how fast you can develop something new. And as soon as you get to that becoming the thing that drives your company, as soon as you get to the speed of development, and everything is driven by software now, the Internet of Things is touching everybody. So if everything is software-based and software takes the longest part of developing anything, speeding up software development is a key thing. It's like a universal good for all businesses now. And what I'm seeing is cloud is part of speeding up. It's not the hell thing, but it's part of speeding up software development. And that is a general thing that everybody is figuring out how to use.
So let's try, or I will try to not turn this into a business podcast, though that would be interesting. But still, I want to ask if you look at those three things, like the growth, driving down cost, and speeding things up, then it seems that your opinion is that the cloud optimizes for growth and speed, and not so much for cost. Is that? Would you agree with that? It depends where you start.
There are a lot of companies that have very overburdened, bloated costs in their infrastructure. They have like an incredibly complicated SAN storage system with very high cost vendors in it. If that's your environment, then going to public cloud is usually lower cost because it's built. It's a switch to a commodity framework, commodity hardware you can buy by the hour. You don't have to pay a lot up front, and you get a lot more software constructs and a lot more open source constructs in there. So if you're making that transition as part of the cloud transition, then it's also usually a cost reduction. If you look at, I could build this, low cost commodity hardware with open source software on it and stick that in a data center somewhere, then the costs end up being kind of what you're doing and how you're doing it and how much capacity you need to buy when. But it's certainly possible to build things that are cheaper than the cloud, but you have to build it in the same way that the cloud is built. And a lot of enterprises just aren't built that way. Their intrinsic costs are, if you take the number of machines they have and their total IT budget and divide the two, you find that they're paying many dollars per hour per a machine that they could get for a few cents in the cloud.
Mm-hmm. So one of the things that you hinted at was that things are changing from an architectural perspective, from a software architecture perspective as well, if you move to the cloud, that you maybe end up building things differently. What are some of the things that you think are different once you decide to move to such a cloud-based infrastructure?
You can use cloud as just a faster way to do data center stuff, and that misses most of the benefit, I think. The real benefit comes when you start doing things that you could not have done in your data center. You can trivially do hardware experiments that last a few days on a huge scale, scattered all over the world. Something that you wouldn't even go to your ops guys and say, hey, I need a globally distributed database with 100 nodes in it and a couple of 100 terabytes of solid state disk. And I'd like it this afternoon. And 6 different data centers and whatever. We did this without asking permission. It took about 20 minutes to create when we were at Netflix. We were trying to run an experiment to build a very write-intensive globally distributed database to see what would happen. And it was the decision to do it was while we were walking out of a meeting. The guy I was talking to wandered by somebody else's cube, asked them to set it up. That afternoon it was created. We put 18 terabytes of data we pulled from our backups into it, pushed it across the world, and then hammered the thing as hard as we could with all kinds of error in failure injection to make sure it worked well. And 2 or 3 days later, we removed it. That was 96 machines. Each machine was 64 gig of RAM and 2 terabytes of SSD. You can't do that if you have real infrastructure, because it just takes too long to get approval. That's a multi-million-dollar machine. I don't even know what it would cost, but it was, I don't know, a few $100s an hour was what it actually cost. And for the value we got out of it, then we went to a meeting the following week and said, okay, we just proved this works. And when you go to a meeting with working code or benchmarks, examples, you win arguments. And there was an argument going on about how we were going to do distributed systems and whether we could rely on what kind of bandwidth we could get in a global cloud. And we were running about 9 gigabits of bandwidth in parts of this thing. So it just closed down this whole argument and said, well, this works, we proved it. And everyone went, okay, I guess we can use that. And it short-circuited an enormous amount of what would have been debate and justification and all of the things you'd be doing and arguing with people about how much it would cost and all that kind of stuff.
So that's actually the idea of doing experiments, being able to try stuff out.
We are retiring risks, basically. You're taking things that might not work and checking them out to see if they work. And there are lots of cases where that's been a very powerful technique.
Mm-hmm. Does it affect the actual running production software as well? Did you build it differently because it was running on the cloud, or differently from how you would have built it if it had been running in your own data center? Yes,
it's built to be dynamic, and I know you want to talk about sort of Simeon Army things. This is really where it ties in. There's some architectural principles which people kind of have heard of the chaos monkey. What that really is it's enforcing an architectural principle. And the principle is quite often...
Can you explain what the chaos monkey is? Because I'm not sure everybody knows it.
Well, I'll explain the principle and then it'll be obvious why it makes sense. So there's an analogy going around right now which is about cattle versus pets. And you've seen a few talks on this subject where if there's machines in production that you know their name, and if they go down, everyone gets upset, that's a pet. That's a pet machine. It's like your pet cat, right? You have to take it to the vet if it gets sick. The other kinds of machines are cattle. It's a herd of cattle in a field. You're getting so many gallons of milk. And if a few of them die, you get a slightly less milk that day. You buy some more cattle, right? The principle that Netflix adopted was that everything in production is a herd of cattle. Everything is an autoscaler. There are no pets. There are no individual machines. that if an individual that went down that anybody would care about. So once you've established that principle, you have to test that principle by going around killing individual machines at random, which is what the Chaos Monkey does. It just picks between 9 and 5 during the week. It will just go around stopping machines and saying, sorry, this cow is dead. And the system would then, the autoscaler would then just automatically replace it. And if somebody snuck a individual machine into production and the Chaos Monkey killed it and they got upset, we'd say, we shouldn't have done that, right? So it's in for the architectural principle by having a process there which is sort of forcing the developers to think in this new way. So everything you launch is an autoscale group. Even if there's only one machine in the group, it's got to be a stateless, disposable machine that can be restarted. And they took it to the next level with the data layer is a triple replicated Cassandra backend, and they actually kill those off as well, including the disks that are inside the instances. So you might lose a few hundred gigabytes of data when you delete the instance. It's not an attached storage model. The disks are inside the instances, but it's replaced, and then the data is resynchronized from the other two copies and just keep going. So they're proving that you can build an ephemeral data layer as well. So that's really that's a different way of thinking. From a sort of data center mentality where you'd say these machines should always stay up and you can make perfect machines. Instead of that, you're creating fleets of machines or herds of machines which are extremely resilient because you can lose large numbers of them and everything still works.
Mm-hmm. What did you use to dynamically reconnect stuff? I would imagine that there's something that needs to be registered in the load balancer. There are some machines depend on each other. Whether virtualized or not, to know who to talk to or who is part of the group that they're supposed to talk to. How did you handle that? Did you have to build that yourself, or were you able to use stuff available on the platform?
There's two answers to that. So at the edge, the things that are externally visible, there's a DNS name for a thing, right? You're going to go hit an API at a well-known symbol. So the DNS basically takes a name and spreads it across usually 3 zones in AWS. So that we use the Amazon, or these Amazon Elastic Load Balancer, the ELB. The first level of ELB is a DNS splitter that basically just round robins the requests across the 3 zones. Then the next layer is a set of machines that run something that's logically equivalent to something like HA proxy, and it's you register back-end machines with that. It health checks them and maintains a pool of service machines behind the load balancer, behind a large tier of proxy servers. So that's the edge. And you register into you take an autoscale group and you register it with a load balancer, and the AWS handles all of the machines coming in and out. That's the edge, but when you get inside the system, you want to be able to talk between machines, and you can either do it using like a message bus or something like that. But what Netflix uses is a service registry with a lot of metadata in it, which is called Eureka. It's one of the open source projects, and it's basically just a Java Tomcat server that was dedicated for this use. Everybody calls it every 30 seconds, says, I'm here, this is more information about me, and then another call around about every 30 seconds says, tell me where everybody is. So you get a map of the world back from it that tells you all of the instances and what their names are and metadata about them. So then when you want to call a service by name, you look it up in this map and basically say, I need a service ABC. Okay, there's ABC. I don't care what version I'm calling, but here's the latest version of ABC that's taking traffic. It's up. Here's an instance. I'll go call that one. And you basically... it'll call ones that are in the same zone and things like that. So that's some code that was wrapped around the Jersey library, sort of HTTP client, Java code that was embedded into the client-side code for the platform, which is open sourced as a project called Ribbon by Netflix on GitHub. So Ribbon is the client-side code. And then there's a server-side component, which is a base server, and that's called Carry On with a K. And those two, Carry On and Ribbon, basically work with Eureka to find each other and make all of the direct calls in a very highly available, very flexible way, and with a lot of options on how you can route traffic.
Okay, so I would love to spend about 6 hours talking about just all of those libraries, but moving to somewhat of a meta level, how did you figure out how to solve the bootstrap problems? How does Eureka itself stay up and available and replicated, because it can't use Eureka because it is Eureka, right? How do you?
Well, there's a number of standalone services that just sit there. So the typical arrangement, the way you roll this out is you take an AWS region and you pick 3 zones within that region, because you want to triple replicate everything. So then what you do is you start one copy of Eureka in each zone, and they actually talk to Route 53, the DNS service, and create a DNS. They register themselves in DNS. So there is one well-known DNS rendezvous point that everyone goes to, and that is spread across these 3. So you can go to any of the 3, but it will sort of prefer to go to your local one. And then they have a sideways protocol, so they replicate side to side. So the 3 copies work. The system is actually very robust. It's if you're familiar with the CAP theorem, most coordination services try to be too consistent, in my opinion, and that when you partition the system, they fail in nasty ways, and you can't get a consistent view, so they stop working. Eureka is an AP system. It's available when partitioned. In fact, the system still works even if you kill all of those nodes, and that was something that was developed over a while because occasionally things fail. So basically, you can kill all of the name services, and the system everything still works. It just freezes. You can't create new machines in the service, but everything still runs. And when Eureka restarts, it loads up all its state and rediscovers everything, and you can do that. It's basically built to be extremely highly available and robust, rather than to be as consistent in the same way that something like Zookeeper would be. We looked at basing it on Zookeeper, but Zookeeper has these failure modes which actually make it less desirable.
Can you talk about 60 seconds about the CAP theorem and which parts of it you apply, or which side you leaned to at Netflix in general? Is AP, or you have to explain what it is, and is AP the general way you build things there? Yeah,
I mean, you have to decide at some point whether consistency or availability is most important to you. And as a physicist, everything is actually inconsistent because of Einstein and relativity and whatever. If you go deep into the bowels of the algorithms, but the basic principle with Netflix is that no partition or failure should take out the service. So we definitely lean very heavily on the availability side when things are partitioned, which means if you slice Netflix up and drop all the networks between all the different parts of the system, it actually continues to work the isolated systems will just carry on working, and they will gradually drift and become inconsistent with the rest of the system. And when you reconnect it, there's the last right wins basically takes over. Usually Cassandra kicks in, and whoever wrote the piece of data last ends up overwriting whatever was written in the meantime. So it gradually gets back to being a consistent system, although you may lose a few updates if you modified something and then it got modified somewhere else. It's better to deal with the inconsistency issues than to be down. That's really and for a service like Netflix, where with 50 million people trying to watch movies around the world, they have an expectation when they turn on a TV set that it should just work. There shouldn't be little messages saying, sorry, we're down right now. People, it's hard to tell a 3-year-old that they can't watch their, dinosaur cartoons because Netflix is down.
Tell me about it.
Right.
So I think this is obviously very convincing for this particular use case. Was it something that you applied in the same way when, say, accounting was addressed, or when it was billing and all of those use cases where people typically expect stuff to be 100% consistent because they're so used to that? Or did you universally apply that principle?
The principle is applied to the customer-facing things that could cause an outage in the service. So if you hit the play button, you should get a movie playing. Anything that's in the loop for doing that needs to be highly available. There's stuff in the back end that doesn't need to be highly available. Like billing systems need to be more consistent but they aren't in that play loop, right? For Netflix in particular, the sign-up process, you don't want to drop a customer during the sign-up process, but if you for some reason can't, validate their credit card right now, you can kind of say, well, I'll just let you get the service and we'll validate that credit card, asynchronously. But most of the time you want to do fraud analysis and things synchronously. So there's a few things where you want to be consistent, but they generally are relatively low traffic things that don't affect the service delivery itself. So you partition those things off into a separate space. There's use of things like Zookeeper give you the ability to do sort of globally consistent sort of locking and things that look a bit more like transactions and things where you can enforce consistency and leader election, whatever. But generally, you want to avoid that in things that are the customer-facing part of the service, and that distinction is kept fairly clean at Netflix.
Mm-hmm. Makes perfect sense. So one of the things that you mentioned in the beginning of the show is that the original application handling the DVD sending out business was a monolith. And one topic that I know you're interested in is splitting up monoliths into smaller units, these days typically called microservices. Mm-hmm. Did you apply that principle at Netflix? And if so, how did it turn out there?
We didn't call it microservices at the time, but what we found was that Netflix at that time had roughly 100 developers building the monolith, and we were stomping on each other's code all the time. And this is a very common problem. There's two problems with the monolith, which, as you scale, become big issues. When there's 2 or 3 guys writing some code, it doesn't matter. So people generally start off building a single monolithic application because that's the fastest way you can get something done. And then at some point, your organization scales, and you want to, and a few other different attributes kick in. So one of these aren't bad. It's just that they are hard to scale in large organizations. So just be clear on that. So the problem we had was two problems. One was that everyone was trying to modify the movie object, and everyone was trying to modify the customer object in just about every code change that they made. And so when you developed your code, you wrote a bunch of jar files, and then QA would pick up these jar files and try and integrate them all the branches into the next version of the code that you were going to roll out. And they just have all kinds of collisions and problems, and it'd be back and forth. So it took longer and longer to get the code delivered because the integration phase got harder and harder, and the QA guys became a bigger bottleneck because everyone was breaking each other's code. So that was one problem. The fix for that is to separate out the code and decouple the teams so that each individual engineer, instead of developing a jar file that depended upon everyone else's jar files in a very intimate way, was developing a service that had very clear connections over REST calls or whatever, had a very clear set of interfaces to everyone else's code. And so that meant that the tangling together of all of the objects couldn't really happen because they were all in different address spaces.
Mm-hmm. And how many of those things did you end up building at Netflix? I'm not looking for an exact number. Just is it dozens or hundreds
growing. Or? So, well, it's just to go back to the other reason that monoliths are a problem is if you're trying to roll a weekly or bi-weekly update that's monolithic. That Netflix was on a 2-week train release model, and something broke and you had to roll back. The 99 other things that were that release also got rolled back because they were part of that release, right? So one broken thing blocks everything else. So that's the other problem, right? At the operational delivery point, rather than the QA. This is rather than the QA team blocking. This is what happens at the ops level, right? So breaking things into separate pieces that can deploy independently breaks that problem because now you're not blocked by somebody else's bug. So everything becomes much more fluid. So what happens is you get a few hundred engineers, and they individually are building their own service. And so fairly rapidly, you have a few hundred services. And Netflix now has maybe 500 to 1,000 services. And then there are multiple versions of those services running as well, because you don't shut down the old version of something when you start the new one. Because now you've already got this layer, this metadata layer in Eureka, handles the routing of traffic between things. And it knows about versions. So if you have a service that depends on version 3 of some other service, version 3 of that service will just always be there, even if a version 4 comes along, and version 5 comes along, and somebody else wants a new feature of that service. So they're using version 5, but it doesn't disrupt the fact that you're now talking to version 3. Right. At some point, you upgrade to a new version, some libraries where you stop using version 3 and you switch over to version 5. But it decouples the deployment of new code from the retirement of old code. You can always deploy new code synchronously, and you always retire old code asynchronously. And it's this kind of sometimes called the immutable server or immutable code pattern, because you don't modify code in production. You start a new server with a new instance of the new code alongside the old code. The problem with this, of course, is that your architecture diagram looks like something I call the Death Star. It's a huge number of icons with lines between them in a big circle, and there is no simple architecture you can draw anymore. But it reflects the actual flow of the business, and you can pick up an individual service, and which is really what matters, because if you talk to Eric Evans about domain-driven design, he may have been on SE Podcast at one point, but there's a concept called bounded context. What you're doing with microservices is you're creating a bounded context that says, these are the consumers of my service, these are the dependencies of my service, I don't need to know about anything beyond that. And I can develop this service and I can iterate it, and I'm not coupling that to lots of other things that actually have nothing to do with me. So it becomes much more productive for developers to only be able to concentrate on this bounded context.
How does the number of services and the fact that you have them in multiple versions and the fact that they're connected and collaborate to provide some customer-facing capability, how does that affect the analysis of problems? What do you do if something goes wrong? Isn't it incredibly hard to find out what actually happened because you have those many moving parts?
It sounds more complicated, and in some senses it looks more chaotic from the outside, but it's actually easier to find out what's going wrong. Because if a jar file breaks in the middle of a monolith, it's very hard to figure out what actually broke. Everything is tangled together, and you typically have to get we used to have these emails to everyone in engineering saying, this build's broken, we can't figure out why, can everybody have a look and make sure their stuff's okay? And this is one of the reasons why we went to microservices. You now have a failure boundary that says this service is broken. You make a call, it gives you an error. Okay, that's obviously broken. Or it's running out of memory and blowing itself up because you've got some kind of memory leak, GC problem, garbage collection problem. Or it's got a runaway CPU bound problem. All of the kinds of problems that could go wrong are now contained to a certain version of a service class. So you look across your system and say, this particular service is now spewing a huge number of errors into its logs. Something's wrong with it, right? And then who wrote that? Okay, I know that guy. Go call him. So there's a call tree set up in PagerDuty for every microservice. And then there was the problem with this, though, is that the failures tend to occur one level up from where they're caused. So if you have a service that's broken, the services that depend on it will tend to break. And what happened was an interesting effect, which is that the API front end ended up being on every single call, because everything that broke happened, appeared at the API, and then you'd have to dig back into the dependencies to find out what had really gone wrong. So the API team decided that they wanted to build a system that would point a finger at people and tell them that it had broken. And this is actually become a fairly popular tool. It's called Hystrix, and it's a circuit breaker pattern. Something that actually what actually happened was I gave them a copy of Michael Nygaard's book. I really said, read this, and they basically went and implemented a bunch of patterns. So what we needed to do was build bulkheads and circuit breakers, and this turned into a very, very useful way to do it. So once you have circuit breakers, the API server can wrap all of its dependencies in circuit breakers, and if it sees a bunch of problems, it will flip the circuit breaker and put up an alert that says, I'm not broken, but this guy's broken. So this points the finger. That goes out to PagerDuty. The API team gets to sleep at night, and whoever wrote the broken dependent thing gets the call. And that just came out of this self-preservation mode of putting, and this is like not being able to externalize your problems to operations people. It's just because the developers are on call. They learn to build robust code. They learn to build systems that point fingers at the right problems, and you get very debuggable systems. And this is part of the sort of, you can think, well, if I make something somebody else's problem, I don't have to deal with it. But it's actually better to have the problems come directly back to you so you don't cause more problems. And that's a different way of thinking from the typical sort of enterprise developer. Turns out you actually end up sleeping better at night because your code doesn't break, and it actually takes less time to fix it and build it and run it yourself than it does to explain to the ops guys what you've done, particularly in a continuous delivery model where you're updating your code several times a week maybe, or several times a day.
It's also a lot more fun, right?
Well, it isn't fun to be woken up at 4 a.m., but
probably true.
It's very unlikely to happen if you're competent at what you're doing. So people that can't figure out how to build reliable systems probably shouldn't be working for you, is another way of thinking about it.
So you've mentioned a number of things, some by name, some just by concepts like continuous delivery and DevOps and of course the cloud and now microservices. How much do you think those things are related? Is it like they're completely orthogonal and they just go together pretty well, or is one a prerequisite for the other? What's your view on this connection?
I think in the modern world, where everything is software-based and time to deliver product matters, continuous delivery is really becoming a competitive advantage, a disruptive advantage. If one company is doing, 10 deploys a day and another company is doing, one new version every 6 months, one of those companies is going to learn and develop and come up with a far better product much more quickly. And that's the transition a lot of enterprises are struggling with, to a more SaaS-based continuous delivery model. So once you're trying to do stuff, you can get up to maybe once every 2 weeks with a monolithic app, and if you're Etsy, you can do it multiple times a day, but it's quite hard to do. If you look at if you're really trying to get a monolith going fast, you should study very deeply what Etsy have done to do that. And what they've done is amazing, but what most people want to do is spread the concerns around, and have more distinct bounded context so that everything can move independently. And once you get the independent teams can have a product manager, they can have all of the development that works on that piece of that product, and they can have whatever DevOps person or delivery person they want in that team. And that team can then deliver independently. And that's a DevOps organization kind of team, or Amazon call them 2 pizza teams or whatever, but they own everything from figuring out what they should be doing to delivering it. And everything else around them is an API. You get a very high trust within that team, and everything outside the team is an API call. It's a relatively untrusted external sort of fabric that they're running on, and you don't assume that any API call you make outside your team is going to succeed, if you see what I mean. So there's a sort of a trust boundary in this bounded context. And that is really the DevOps model, and that's the reorg that most people have to go through to get to DevOps, because you no longer have tickets and handoffs between silos where you talk to the storage guy, you talk to the network guy, you talk to the sysadmin, and there's all these different teams in operations that you have to walk through to get something done. This is a cross-cutting team which has APIs for doing that. So that's really why cloud and DevOps, from my point of view, sort of work together. I mean, there's DevOps for just optimizing the interface between development and operations. But what I think is interesting is taking, and there's really 2 approaches to DevOps. You can be an ops person that is getting better at automating, doing infrastructure as code, and you start developing, right? So think of it as an ops people starting to develop and building a better interface to the development processes. From the other direction, which is really where Netflix came from, was development people learning to operate and using a cloud as the automation layer to provide the infrastructure to automate. They kind of meet in the middle with some similar tooling, but actually occasionally slightly different concepts.
With some of the libraries that you mentioned, Eureka and Ribbon and Carrion and all of those, it's quite obvious that Netflix invested a lot of time into making the platform usable for its own purposes, but you also open sourced a lot of that stuff. What was the reasoning behind that? Was there a pure business reason? Was it to get collaborators? What was the intention of doing that?
There's there's a whole series of reasons, and there were some that came up that we didn't expect. I did a whole presentation on this at one point, and there's 4 or 5 different things. But the initial thing was that we were making a transition from depending upon vendor-based code. We went and bought Aqualogic from whoever made the Aqualogic message bus, which ended up bought by Oracle or something, and then you get support issues, and So no, we don't want to be dealing with enterprise software that we pay a lot of money for, and we actually figured out we were getting better availability and support from the open source world. So we wanted to switch to an open source based business model where all of our code we were using to build Netflix was open source. And we decided we wanted it all to be Apache licensed. So we set up a relationship with the Apache Foundation. We got our lawyers to talk to their lawyers. And what came out of that was an agreement that any engineer at Netflix could use anything that was Apache licensed without just talking to anybody. You could just download it. We understood what that license meant. It also, you could contribute fixes to any Apache project without having to go to get approval from anybody. It just, it sort of institutionalized the ability to interact with anything that was in this sort of license umbrella. And then when we open sourced our own projects, there's actually some intellectual property things where any patents that Netflix has around an open source project are actually written into the project itself as it gets open sourced. So you're basically building a defensive patent posture around the fact you've open sourced a piece of technology. So that's the sort of the groundwork for doing things. And that was just because we wanted to be part of that community, and we wanted to be able to not only just give back things that we thought would be helpful, but also get our fixes to be part of the mainstream. Because you don't want to continually have to keep rebasing your branches, back into some piece of software that's moving on. You want anything you contribute to be part of the mainstream product. So that was the initial reasoning. The secondary reasoning was we wanted to be able to hire better developers, and the really good developers have open source projects in their names. Some of the really best developers in the world have gone and built amazing things, and you go, I want to hire that guy. They want to be able to see that Netflix is a nice place for building software that is open sourced. So they feel comfortable moving to Netflix because Netflix is very supportive of whatever they're building as their side project. Third thing was this was not sort of expected, but a much stronger short-term effect than you'd think. If you go to a developer and say, could you clean up your code? It kind of always goes below the bottom of the list of things to do, right? If you go to a developer and say, would you like to open source your code? Cleaning it up turns into the evenings and weekends highest priority, right? Because they're going to have their name on that code on GitHub. That's going to be part of their permanent resume. They want it to look good. So some of the biggest code cleanup, documentation, isolation, taking code that's a bit tangled into Netflix and bringing it out to be a separable thing that's kind of better thought through, cleaned up interfaces, code quality, all kinds of things. It's a fantastic way to actually improve the code quality that you use. Because a lot of the stuff people have in production really is a lot messier than they'd like to admit, because it was just put there to do something, right? So that turned into a short-term business benefit. And then the longer-term benefit was you can start hiring from people that know your code and they know your architecture. You can go and look at, who are the people that forked this open source project? Okay, let's go look at who's most active. Hey, do you want a job at Netflix maintaining this code that you seem to be sort of maintaining anyway, right? It becomes a way to find interesting people to recruit, and that's happened quite a few times as well.
Mm-hmm. Taken together, all the stuff that you've open sourced is something, or could be maybe called something like a platform offering on top of Amazon's lower level infrastructure offering. I don't know whether you agree with that.
Part of it is
assessment. But, so, how do you propose other companies go about that? Should they all be just using Netflix's stuff, or is it a reasonable expectation for a company with not as many developers to develop their own stuff? How do people choose how to approach this?
I think there's probably 3 different classes of things in the Netflix open source GitHub account. There's 45 or so projects there now. It's a bit hard to navigate. They've kind of tried to make it a bit easier to find things there. There are things which are specifically in an AWS-based platform. You could look at it as kind of a scalable cloud foundry. It's a disaggregated, scalable platform for doing the same kinds of things that things like Cloud Foundry do. It's, your developer buys into this platform, you deploy it, and you can get very productive developers deploying code globally very simply. So that's one class. Then there's a bunch of tooling that is really standalone, has nothing to do with that particular platform. Like there's a cost monitoring tool called ICE, which is very nice. There's security tools that are just standalone. There's a Ruby on Rails app that they just came out with called Scumbler, which goes and finds people out on the internet that are talking about doing bad things to your company, and notifies the security team to do takedowns of DOS attacks or YouTube videos telling you how to do bad things, like steal accounts or whatever. Those kinds of things. So this is a standalone tool. It's got nothing to do with the platform, but it's a useful thing. And there's a lot of stuff there. And then the third one are the things that really nothing to do with cloud. There's some algorithm things. There's libraries for making Zookeeper better. There's quite a lot of useful bits and pieces that have been contributed. There's a big data pieces. There's a closure library for talking to Pig, I think, called Pigpen. Somebody came up with it. Hey, this is useful enough to stick on GitHub. We'll put it up there.
Okay, so maybe let's switch to another topic and talk a bit about what you do these days, because you're no longer at Netflix, as you mentioned. You're now part of an investment company. What is the stuff that you do, that you spend your days with?
So to some extent, it feels like what I was doing at Netflix was the overall architecture role. I spent a lot of time talking about Netflix publicly, and some of that was to try and get Netflix to be better known so that we could hire better engineers. Some of it was to make sure that the patterns that Netflix developed didn't end up in some kind of dead-end backwater and everyone else went off and did things a different way. It's sort of future-proofing the architecture by spreading it around and creating a larger number of people doing things the same way. So those were sort of the reasons for that. I also spent a lot of time talking, when I was at Netflix, talking to venture capital people that were talking about, hey, I've got a new startup with a new idea. What do you think of it? And I've sort of taken those two things, which were sort of the spare time activities effectively in a architect role, and made those into my day job. So what I do now is I spend all my time talking to startups about new ideas, and I spend even more time doing talks at conferences. And this fall I'll be at, I think, Go to Berlin and Go to Aarhus and Copenhagen, and there's a web summit in Ireland, a few things in Europe. More conferences. I forget all the different conferences I'm at.
So what are some of the things that you learned there? How different are other companies from Netflix?
I think what's happened is enterprises are trying to figure out how to build web services. That's it's something they haven't necessarily had to do before. And one of the big drivers for that is you kind of think of it as sort of the Internet of Things starting to happen to companies. One of the companies that's been talking to Netflix a lot is Nike, who have the back end for their Fuel Band, which has a lot of customers running around, literally, and they have a lot of traffic from that. So they've been looking at using Netflix open source to build their back end. Surprisingly, IBM is one of the biggest users of Netflix open source. They needed to develop a whole bunch of services to make SoftLayer, after they bought SoftLayer, to make SoftLayer more resilient and add more features. And they started using Netflix code for that. There's quite a few companies that started adopting either the code itself or the ideas and the patterns around it. And if you look at it, and then I'm starting to, there's a lot of buzz around Docker right now, and I listened to Solomon talking about, why he did Docker and the way that they think about it, and I'm listening to the same kind of architectural principles that I've been talking about, which is that you bake code into immutable images, which you then deploy, which is the same idea that Docker has. And you're deploying these sort of rapidly deploying that very dynamic infrastructure. So there's an interesting overlap here in that there's a whole Docker ecosystem that I'm playing around with and trying to understand and talking to everybody in that area. So that's been sort of microservices going mainstream to some extent, or the microservice concept going mainstream is very well aligned with the things I was doing at Netflix. And that's been a lot of what I'm doing now. On the other side, we have these portfolio companies that Battery Ventures is invested in. If you run distributed Teams, you use a lot of video conferencing, and one of the companies in that space is called Blue Jeans Network. They have a multi-protocol video conference that can connect together all different types of hardware rather than you being locked into, like, everyone's on Skype or everyone's on a Hangout or everyone's on Polycom or Cisco or whatever. They can glue them all together into a single session, a single conference call. And they've announced Hangout support, but I don't think it's quite shipping yet. That's the next shipment. So you'll be able to do a Hangout into anything else, basically. I'm working with them. They're growing really fast. So I'm working with them on scaling, on making the system more highly available, and speeding up the development processes so that they can do releases more often, moving to a more microservice architecture, potentially moving from a MySQL-based monolithic database backend to a more distributed NoSQL. Probably, we're looking at Cassandra and things like that. We're still investigating what's the right technology, but that's a fun project for me because it's like I'm back to being a cloud architect for Netflix, but it's sort of two-way video instead of one-way video.
Speaking of lock-in, what is your recommendation regarding lock-in to any particular cloud vendor? Is this the new kind of database lock-in that everybody needs to avoid, or what are some strategies to address that?
Actually, database is a good example. I'm not sure if anyone ever really said, I'm going to write this schema in both MySQL and Postgres or DB2 and Oracle just so I don't get locked into one or the other. I don't think that ever really happens. Somebody picks a technology.
Product companies might do it, right?
Yeah, but
enterprises don't do it, but product companies might have to do it because they run on different databases from the beginning.
Yeah,
but I agree.
There are many products which are really portable across databases, and they end up building to lowest common denominator. So you tend to pick the best product you can find that best fits your need, and then you use every feature it's got. I mean, that's sort of the more developer mentality. The operations mentality is I want multiple suppliers because if I get locked into one, they'll put the price up on me. And that's an ops mentality. And those two meet in the middle and in a big argument usually. What I see is cloud is another case of that. The ops guys want more than one cloud vendor so that they have some leverage. And I think if you're an enterprise, you're already a Microsoft customer, and Microsoft Azure is a natural vendor because there's a lot of Windows in your environment that you want to put in the cloud, and that's where the best support for Windows is. And you're most likely with AWS because they're the biggest cloud and the best support for Linux-based things. And you can do Windows on Azure, and you can do Windows on AWS, and you can do Linux on Azure. So you sort of have a second source strategy. So what I'm seeing is most enterprises are doing dual source between AWS and Azure, and then startups. They're typically going to Google and AWS and saying, okay, who's going to give us the best deal? Who's going to give us if you're a startup, you don't want to spend any money. And there are these startup hacks where they'll give you free machines or discounts or whatever. And there's a lot of leverage there. Both Amazon and Google are very keen to have startups on their environment. And it makes sense to play them off against each other and get a good deal. And that's always been that case, back in the old days. You'd be saying, am I going to use, Sybase or Oracle? And you'd beat the vendor's price down by, prototyping both of them or something. So there's really no change there. When you get to it, though, you're going to be most productive using a single vendor because you can use all their features and you can get a lot done more quickly. And speed of development matters more than cost optimization for most people. And then the other thing is that you aren't locked into a vendor that's putting the prices up. And this is something that I think a lot of ops people haven't got their heads around, really. They keep saying, well, if I get locked into AWS, they'll put their prices up. And they keep cutting their prices. And the fact that Google is out there is causing Amazon to cut their prices, Azure and everybody. So what you're looking at is approximately a halving in price every 18 months. So if you're looking at a 3-year cost of a system, you've got to assume that its cloud cost is going to be a quarter in 3 years of what it is on day one. There's a cost reduction curve. So the penalty of being locked in is actually much less. I think the key thing really is if you're trying to roll out something really big and complicated, you need to be in a large cloud. You need to be a small fish in a big pond. If you're running something really small, then there are a lot more vendors you can pick from. You might, if you just want 2 or 3 machines, you probably just as well go to DigitalOcean and pick up a few small machines. If you want to run tens of thousands of machines, your number of clouds you could go to is dwindling to just a few.
What would you say regarding arguments that if you're in some of the business that, let's say, Amazon or Google do business in as well, you're sort of working together with your competitor? Let's say you're a bookseller or a retailer in general, and you're skeptical about moving to Amazon. What would be your answer to those concerns?
Yeah, there's a lot of retail companies in the US that refuse to use Amazon, and they're hobbling themselves by trying to build their own clouds. And they have these internal teams trying to build something that's doesn't scale, it's got fewer features, it's not as stable. And then their product is running on top of that, and they're suffering from that. So you're kind of limiting yourself. Netflix is a classic example of this. So Amazon Prime is a direct competitor to Netflix, and it's a movie streaming service. And if you turn the question around, it maybe makes more sense. So if Amazon Prime running on AWS and Netflix wasn't, then Amazon Prime would have an advantage over AWS in that it's running on the best cloud there is, right? The largest scale, lowest cost, whatever, most globally distributed cloud. So by Netflix using AWS, it neutralizes that possible advantage that Prime would have. Right. And then the other thing is that by becoming a very strong customer, a very public customer of AWS, Netflix actually gets preferential treatment from AWS. And by being very agile and very advanced in how it uses cloud, you could argue that it's actually using cloud in some ways better than Amazon Retail is. So you get to use the features of your competitor against them. Think of it as sort of a jiu-jitsu move. Use the weight of your opponent against them. So that's not, most people don't think about it that way, but I think that's kind of how Netflix sees it. They're certainly conscious that they are depending upon a competitor, but so far Amazon Prime is about 1.5% of network traffic in the US, and Netflix is about 34%, so it's about 20 times bigger than Prime, so not a huge competitor from that point of view. The biggest competitor is actually YouTube, which is about 1/3 of the traffic of Netflix, 1/3 to 1/2. And Google is a competitor, but Netflix also works very closely with Google. So you end up in this co-opetition thing where in the modern world with large conglomerate companies, you just have to work with your competitors and try to use whatever leverage you can against them for your own advantage.
Maybe finally, because I'm German, I have to ask this: what do you say to security concerns that people might have regarding their movement to some cloud service?
I thought you were going to ask me about Netflix launching in Germany. The security is another one of these things where, if you look at the way you used to do security, it doesn't work in the cloud, and some people get upset about that. The people that are excited, though, are looking at things you can do that you could never do in the data center. And there's something about having programmable infrastructure that you can introspect the entire state of it that makes you can make strong assertions about your system. And if you took a typical data center and say, I want to know every external way into that data center, and you'd miss some. There's some storage array that's got a modem that's calling back to a storage vendor. There's all kinds of little extra things going on that you don't really know about, or you can't find, or are sort of sneaking around the back, or somebody put up a machine somewhere. It's very hard to correctly manage every possible way in. if you look at a cloud, you take an AWS account, you say, okay, give me a list of all the instances, iterate across them. That's the IP addresses of every instance, public IP, and then here's the ELBs, the load balancers, here's the elastic IPs. Then you're done, basically. There's a few very well understood things you can iterate over, and you can make strong assertions about them. Netflix has a security monkey that it open sourced, which actually sits there and looks at all of these things. It looks at the security groups you've got installed and tells you you've got things in an insecure state, and it just dynamically tracks that. And it's very hard to build those kinds of things in a cloud, unless you have a cloud-based environment. But you can't plug a tool into the spanning port of a switch and gather all the traffic and do detection on it. You have to build things in other ways. So there's a whole new set of vendors and tooling, and actually Battery Ventures has been investing in some of those companies in that space. It's actually one of the hot areas for cloud development.
Mm-hmm. Okay. So in closing, how would you recommend our listeners go about familiarizing themselves with all of this if they want to play around with stuff? What's a good place to start? Because this can be overwhelming at times because there are so many interesting things to look at. What's a good place to start with?
I think that one of the benefits, so going back 4 years to when Netflix started, we had to make stuff up. I mean, we were reading white papers and inventing things and having arguments and trying things out. The situation now is that everything is much more mature. The patterns are much better understood. The tooling is much more sophisticated. And I think probably the best place to start right now, if you're just starting from scratch, is to just look at Docker and build out from there. It solves 4 of the interesting things which Netflix was trying to solve for. And Netflix is just starting to use Docker itself. But if it was around 4 years ago, we'd definitely have been using it. One of the things it does is it gives you very fast deployment. You can stand up a Docker container in a few seconds. The second thing it gives you is portability. You can build containers on your laptop, and you can deploy them to multiple different clouds, so that you've isolated the code, and you're building these immutable chunks of code, applications, microservices, basically. The third one is that there's an app store, effectively. There's a Docker hub. You can download there's 30,000 different Docker containers that you can just download and use as your starting point. That is something we've never really had, a portable microservice store. You can just download stuff and go play with it. And the last one is that it sort of replaces the need for something like Chef or Puppet, in that the configuration is baked into the container, and that is what is deployed. You're not modifying configuration at runtime. You're creating a configuration at build time, and then you're just deploying it. So I think that embodies a lot of the architectural principles that Netflix came up with. Everyone sort of discovers these things independently, but the Netflix stuff is around that. So I think I'd look at that, and the other place, obviously, go to the Netflix tech blog and Netflix open source GitHub repository, and just try and understand what's there. Look at what Twitter's got, look at what Facebook's got. The best software you can get now is open source, and it's from the large web-scale vendors. That is the best software in the world. It's the most advanced software. And the enterprise vendors that you pay lots of money to have built products that don't scale, that are evolving too slowly, and that don't solve these big distributed problems. So I think it's a really interesting time. You can go build something incredibly quickly, incredibly cheaply, that will actually be scale and be highly available. And I think that's something you just couldn't have done 5-10 years ago. It's a fun time to be out building things.
Okay. Adrian, thanks a lot for this conversation. It was a pleasure to have you on our show. We'll have lots of stuff in the show notes for our listeners. And thanks again for being with us.
All right, thanks very much. Thanks for having me.
We want to know what you're thinking. Please go to iTunes and leave a review of the show. This is Stefan Tilkov for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or Slashdot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.